morning all. My name is Lokesh Soni. I am working as an assistant professor in the Ajay Kumar Garg Engineering College, Ghaziabad. And this is the first lecture of the digital system design, which is the number system. First of all, the content of my presentation is introduction to digital system, then followed by analog versus digital number system, convert the other number systems into decimal, and conversion between octal and binary, conversion between hexadecimal and binary, and conversion between octal and hexadecimal, followed by the fractions. First of all, why we need a digital system when the nature is analog? So the answer is that digital electronics is the field that involve around the digital signals. That means they are the discrete in time and magnitude. The main characteristics of the digital signal is that they are easy to manufacture. Digital circuits are easy to manufacture and they are less costlier than the analog signals. Third point is that a digital signal is an electronic system designed to manipulate the logical informations. That means digital signals are basically represented by the binary numbers like 1 or 0, true or false, like that. So there is only two values. Digital systems are used in everywhere in daily life like communication, traffic control, spacecraft guidance, medical treatment, weather monitoring, internet and so many other things. Recently, nowadays we are using the mobile phone, digital television, digital cameras, smart watches. These all are digital in nature. Digital electronic circuits are usually made from the large assembly of the logic gates, and these are fabricated in ICs, package form. IC is the integrated circuits. There are thousands of millions of the logic circuits or the other circuits are designed. So this is in this PPT I'm going to explain analog versus digital. So we know that when we are talking, the video signals, audio signals all are analog in nature. So why we need digital? So what the most convenient way to represent and transmit the information electronically is a digital. Because for example, analog is continuous in nature. So if the noise arises at a one point in analog signals, it will go from one point to another point. So it will keep on increasing the noise because this is continuous in nature. Whereas the analog signals were used in the many systems to produce signals to carry information. These signals are continuous in both, as I have explained earlier. Analog signals are continuous in both magnitude and time. So in short, analog signals, all the signals are natural or come naturally are the analog signals. As I have explained earlier, like audio and video signals are all analog in nature. And digital signals are unlike the analog signals, digital signals are not continuous, but signals are discrete in value and time. That means digital signals are discrete in time and magnitude. There is no continuity in the signals like the pulse. And the signals are represented by the binary numbers or consist of different values. For example, like this is a pulse signal, this is a discrete in time. Here the value is 0, here the value is 1. Whereas if we are talking about the analog signals, signals is the sinusoidal signal like this, which is continuous in time and magnitude. This is a x-axis is the time and y-axis is the magnitude. Let's say represented by the V, voltage. So as we can observe that this is the continuous in time. Here this is a t1 time, t2 time, t3 time, t4 time and so on. Whereas this is a digital signal which is discrete in time. So if noise is impacted on the, let's say, t1 time, so it will keep on going along with this analog signal because this is a continuous in time. So the noise will also keep on increasing in the analog signal. Whereas in the digital case, if the noise arises at the one point, like let's say here, it will not propagate to the another pulse like 1. So this is the basic, the most important difference between the digital and analog. This is the difference between the analog and digital signals. As I explained earlier, analog is continuous signals, whereas digital is discrete in time and magnitude, represented by the sine wave. Digital signals are represented by the square waves. Like analog signals like human voice, natural sound, analog electronic devices are the examples, whereas for digital signals, computers, optical drivers and other electronic devices. These are continuous range of values, whereas digital are discontinuous values. Analog signals are used in analog devices, whereas digital signals are used in digital electronics like mobile phones and computers and so on. So, this is the analog signal, as I explained earlier. This is the continuous in time and magnitude, which is not discrete, whereas this is the digital signal, which is discontinuous in time, like 0, 1, 0, 0, 1, 0 and 1. And this is also a digital signal, which is one is synchronous, another is asynchronous, which I will explain in the upcoming lectures, what is synchronous and what is asynchronous. Digital signals and information very well represented by the physical quantity. As I explained earlier, the digital signals take the values on the discrete, like, and the digital signals are basically represented by the binary values like 0, 1, true or false, on and off and so on. So, there will be only two values. Next topic for my presentation is the number system. What is number system? Code using symbols that refer to a number of items. That means in digital electronics there are various type of the number systems to represent data. For example, as we can observe from this diagram, like number systems are classified into decimal numbers, binary numbers, octal numbers and hexadecimal numbers. Why it is called a decimal number? Because there are only 10 bits, like from 0 to 9, there is a 10 bits. That's why it is known as the decimal number. For binary numbers, there are only 2 bits, 0 and 1. So, that's why it is a binary in nature. Octal numbers means 8. So, there will be only 8 numbers from 0 to 7. Same for hexadecimal. Hexadecimal numbers are containing the 16 bits, like from 0 to 15. But in hexadecimal, 0 to 9 are represented as we are represented in the other number systems, but from 10 to 15 they are represented like A to F, like A is 10, B is 11, C is 12, D is 13, E is 14 and F is 15. In decimal number the base is 10 because its name is decimal, that means contain 10 bits, that's why its base is 10, which is represented like this. For binary system, the base is 2, which is represented like this, base is 2. For octal number, base is 8, so we can represent like 8. For hexadecimal number, the base is 16. So, for binary number systems, we can using the weighted codes like 8, 4, 2 and 1. How these weights are coming? For example, in digital systems, all the weights are coming on the power of 2, like 2 to the power 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. 2 to the power 0 is 1, 2 to the power of 1 is 2, 2 to the power 2 is 4, 2 to the power 3 is 4, 8. So, we want to represent like if for 8 the binary value is 1, for 4 the binary value is 1, and for 2s and 1s binary value is 0, 0. So, that means if we can add the 8 plus 4, it will give the 12 in decimal. Binary to decimal conversion. For example, we are having this binary number. As I explained earlier, the binary numbers are represented by the power of 2. So, this is 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, 2 to the power of 5. 2 to the power of 5 is 32, which is 1 at this place. So, 32 will be there. 2 to the power 4 is also 1. So, 16 will be there. Whereas 2 to the power 3, 2 to the power of 2, 2 to the power of 2, these two are 0. So, we are mentioning as 0, 0. Whereas 2 to the power of 1 and 2 to the power of 0 are 1. So, we are mentioning the 2 plus 1. So, if we add this number, we are getting the 51 in the decimal. So, that's how we are converting the binary number into a decimal number. Next is that, let's say we are having a binary number 110011. That's this example we have already discussed in the previous slide. So let's move to our next slide. How we convert this number 11001011. This is a binary number. So first of all, we have to take the 2 की powers, 2 की power of 0, 2 की power 1, 2 की power 2, 2 to the power of 3, 2 to the power of 4, 2 to the power of 5 and 2 की power of 6. So 2 की power 6 is 64, 2 to the power of 5, 32, 2 to the power of 4, which is 0 given, so I have mentioned 0 here. So the in binary form, whereas the 1 is represented at the place of the 2 power, we have to take that number only. So 2 to the power 3 is 8, so I mentioned 8 here. 2 to the power of 2 is 0 given, so I mentioned 0 here. 2 to the power of 1 is 2, 2 to the power of 0 is 1. So after adding all these numbers, we are convert this binary number into a decimal number, which is 107 in decimal. So that's how we can convert the binary number into a decimal number. We have to just take the power of 2 to the power of that number, which is 1 in the binary digits. Rest will be 0. Convert the other number systems into a decimal. For example, I have a number system like whose base is B. This is a general form. So if I am having a number system whose base is B and I want to convert this number into a decimal, then how we can convert it? So as we can observe here, if the number is like this, x to the power n minus 1 to x1, x0, and this is a fractional part, x to the power of minus 1, x to the power of minus 2 and so on. So before the fractional part, we are moving from right to left. After the fractional part, we are moving from left to right. And if we are converting some base to the decimal, then we have to multiply this base powers. Like for x0, the power of the b is b to the power of 0. For x1, the power is b to the power of 1, b to the power of 2 and so on. Whereas after the fractional part, the powers are in the negative form, like b to the power of minus 1, b to the power of minus 2, b to the power of minus 3 and so on. So that's how we can convert any number system into a decimal number. For example, we want to convert this number 110.11, whose base is 2, into a decimal. So how we can proceed? As I told before the decimal, we have to move right to left. After the decimal point, we have to move from left to right. And we just multiply the power of the base by positively from right to left, and from left to right it should be a negative. So 0 into 2 to the power of 0 plus, if we are moving from right to left before the fractional part, 1 into 2 to the power of 1 plus 1 is to 2 to the power of 2 plus, for the fractional part, we are taking the negative powers of the base. So 1 is to 2 to the power of minus 1 plus 1 is to 2 to the power of minus 2. If we are add this number, we can successfully convert the binary into decimal. So this is 0, this is 2, this is 4 plus 2 to the power minus 1 is 0.5, 2 to the power minus 2 is 0.25, which is equal to 6.75. So this is my decimal number. For example, now the base is 8. 8 is the octal. So how we can convert the octal into decimal? Before the fractional part, we are moving from right to left. After the fractional part, we are moving from left to right. So just multiply the power of base to the power of positively from before the fractional part, and after the fractional part it should be a negative power. So we are starting from 8 to the power of 0, 2 into 8 to the power 0, plus for this 2 is to 8 to the power of 1, because our base is 1, plus after the fractional part the power will be negative. So 4 is to 8 to the power of minus 1. If we are add this, we are getting our decimal number. So 8 to the power 0 is 1 only. So plus 8 is to 2 is 16, plus 4 by 8, which is 1 by 2, nothing but 0.5. So after adding this number, we are getting the 18.5. This is our decimal number, octal to decimal conversion. Next, let's say we are having a hexadecimal. Why it is hexadecimal? Because its base is 16. So if we want to convert this hexadecimal into decimal, we are again taking the 16 to the power of 0 plus 1 is to 16 to the power of 1. After decimal, we are getting we have to take the negative powers. 16 to the power of minus 1 multiply. As I explained earlier, in hexadecimal, after the 9, the bits are represented by the A, B, C, D, E and F. So A is 10, V is represented 11. So 16 to the power minus 1 into 11, which is equal to 16 to the power of 0 is 1. So 2 plus 16 plus 11 by 16. If we are add this number, we are getting our decimal, hexadecimal to decimal conversion of this number. Now, if we want to convert the binary number into a decimal, this is a shortcut way how we can proceed. If we are having a 3-bit representation, as I mentioned earlier, we can use the weighted codes. For 3-bit, the weights are 4, 2 and 1. All are 2 to the powers, 2 to the power of 0, 2 to the power of 1, 2 to the power of 2. If we are having a 3-bit number, let's say I have 1 at 2 to the power of 2 place, 0 here and 1 here. So if we can add these numbers, like 1 is at the place of 4, 1 is at the place of 1, whereas 0 is at the place of 2. So if I add 4 plus 1, which is equal to 5, this is a decimal representation of the binary number. So for the place where the binary numbers are represented by the 1, we have to take only that powers. For example, if we are having a 4-bit binary number, so we can use the 4 bits in a binary representation, like 2 to the power of 0, 2 to the power of 1, 2 to the power of 2 and 2 to the power of 3. For example, we are having a binary number of, let's say this is 1, this is 0, this is 1 and this is 1. So if we can add the weights corresponding to the 1 value, we can have 8 plus 2 plus 1, which is equal to 11 in decimal. So that's how we can convert the binary number into a decimal number directly with the use of the weights. Now, if we want to convert the octal to binary and binary to octal, then how we can proceed? Like first we can convert the octal into binary. So in octal, we already know in octal means there we can represent the bits in the 3 weighted codes. So we have to write the each octal digit in 3-bit binary equivalent. How we can write? Like this is a 24.6, which is in octal. So we have to represent each bit in the octal in the 3-bit binary equivalent. So for 3-bit, I have mentioned earlier that we can use the 4 to 1 as a weighted code. So for 2, how we can represent 2? 2 we can represent 0, 1, 0. 4 we can represent 1, 0, 0. 6 we can represent 1, 1, 0. So altogether, if we can combine these 0, 1, 0, 1, 0, 0, dot 1, 1, 0. This is the conversion from octal to binary. We have to just represent each octal bits into a 3-bit equivalent binary numbers. How we can convert the binary into octal? Make the group of 3 bits, because this is an octal number system. So we have to take only 3 bits. So before the decimal point, as I have told earlier, we have to move from right to left. after the decimal point we have to move from left to right. So we have to just pair the 3 bits. So if I pair these 3 bits, so there is only 2 bits are left. So we can append the 0 before it. Like this is our number, original number. So we have to take the pair of 3 bits, and we can, since there are only 2 bits are left, but we need 3 bits. So we can append 0 here. Similarly, on the fractional part, we have to move from left to right. So we are making the pair from here to here. Since there are only 2 bits, we can append one more bits like 0. Because after appending the 0, the number is still the same. There is no difference. So this number is equivalent to 3. This number is equivalent to 3, and this number is equivalent to 4. So our conversion from binary to octal is 33.4. Next is the conversion between hexadecimal and binary. So to convert the hexadecimal number into a binary, we have to take the pair of 4 bits, because this is a hexadecimal in nature. So we have to take the 4-bit pairs. So each hexadecimal bits we have to represent into a 4-bit binary equivalent. Like 1 is represented by 0, 0, 0, 1. 8 is represented by 1, 0, 0, 0. A is represented, as I mentioned, A is equivalent to 10. So 10 we can represent 1, 0, 1, 0. If we are using the 4-bit weighted code 8421. So 10 is represented by, the place of 8 is 1, place of 4 is 0, place of 2 is 1, place of 1 is 0. So if we can add, we can get the 10. And if we can merge these together, we are having our binary number 1000.1010. This is our binary number, hexadecimal to binary. Next, how we can convert the binary number into hexadecimal? We have to make a pair of 4 bits. Like in octal, we were making the group of 3 bits, but this is a hexadecimal, so we have to make the group of 4 bits. These 4 bits are paired, these 4 bits are paired, but there is only 3 bits. So we can append a 0 at the end. Similarly, for the fractional part, there are 4 bits are available, we can group them together. So this is equivalent to 6, this is equivalent to 10, which is A in hexadecimal, this is equivalent to 11, which is B in hexadecimal, and this is equivalent to 10 again, which is equivalent to A. So our hexadecimal number is 6AB.A. This is our hexadecimal number. So after the, from this onwards, I will continue in my next lecture. Thank you for listening.